In the last video, we were given a lot of the information about our function. Now we're going to say, okay, we're starting from scratch. We're just given this one single algebraic equation. We want to go and sketch the graph of this function. So that means I need to go and find all of that information myself. So we're going to start, we want to sketch the graph of this. I'm going to start by looking at f of x and see what I can figure out just by looking at that original function. I look at 3x minus x to the third. That's a relatively nice function to work with because it's a polynomial, and polynomials have a lot of really nice properties. So when we talk about f of x, we probably want to know the domain of that function. Well, we're working with a polynomial here. My domain should be negative infinity to positive infinity. The other thing I would encourage you to think about are vertical and horizontal asymptotes. Those are going to have a tremendous impact on your graph. So I would look for horizontal, vertical asymptotes. Again, we're working with a polynomial. Polynomials have no asymptotes. So I'm just going to make a note to myself, no vertical asymptotes, no horizontal asymptotes. That's really all I think I want to cover from the original function. Once you've got that down, now okay, let's go and talk about the first derivative. So here's everything I know about my original function. I'm going to try and highlight all of the information I think is relevant at the end of each sort of section. And now I'm going to talk about the first derivative, and I'm going to do that over here on the right-hand side, I think. So first I need to find the first derivative. F prime of x, this is just a nice power rule, should be 3 minus 3x squared. And I need to start by finding my critical numbers, my possible partition numbers. So I want to set my derivative equal to 0 and think about where is my derivative undefined. So first I'll say 3 minus 3x squared, that's equal to 0. So here I can factor this, or I can use square roots. Either one will be just fine. 3 equals 3x squared gives me x squared equals 1, and then taking the square root of each side gives me x equals plus minus 1. So I have two critical numbers here in plus or minus 1. I'll also want to look at where is our derivative undefined. Here's our derivative. Well, our derivative is a polynomial. F prime is a polynomial. It exists everywhere, so there are no additional critical numbers that occur from this. So, okay, I've got my critical numbers. What do we do next? Well, next we've got to make our sign chart so that we can figure out where our function is increasing and decreasing. That'll help us decide where are our local extrema. So here's f prime. Let's see, here's f prime, and we said -1 and +1. Those were the 2 points that we found. And I'll take a number in each one of these intervals and plug them into my derivative. I'm going to actually highlight my derivative so that I don't lose it, because we'll be coming back to it a little bit later. Actually, right now. So first I need a number to the left of -1. I'll take -2, f prime of -2. This is equal to 3 minus 3 times -2 squared. 3 minus 3 times 4. This is 3 minus 12, gives me -9. So my first derivative is negative, which tells me my function is decreasing on that interval. Next, I need a number between -1 and +1. So how about f prime of, let's say, 0? F prime of 0, this is 3 minus 3 times 0 squared. This is 3 minus 0, gives me 3. So it's a +3. My first derivative is positive. That tells me my function is increasing between -1 and +1. And I need a number to the right of 1. How about +2? F prime of 2. This is 3 minus 3 times 2 squared. Here I've got 3 minus 3 times 4. This should look familiar. We'll end up with -9 once again. So our derivative is negative over there, which means that our function is decreasing. The other thing that I would do, again, I keep forgetting to do this. I don't know why. I would also include the value of the behavior of the derivative at these two critical points, at -1 and +1. Well, at plus or minus 1, we found those by taking our derivative and setting them equal to 0. So I'm going to put a little 0 above each of those. And what that tells me is that at those points, I'll have a horizontal tangent line. It means my function is differentiable. It means we're dealing with a nice smooth curve here. That's kind of the easiest possible case. So, okay, we've gotten a bunch of information out of our first derivative already. You can actually probably say a little bit more here. Our function is decreasing. So our function is decreasing on -infinity to -1 and 1 to +infinity. It is increasing on -1 to +1. I can also look at some of these and I can say, okay, here is my horizontal tangent. I see a local minimum right there at -1. Here's my horizontal tangent at 1. I see a local maximum there at 1. So I have those 2 points. I know that here I'm going to have a minimum. Here I'm going to have a maximum. I just need to find the y values that correspond to those. And for that, I'm looking at my original function f of x. So f of -1, let's plug that in first. This is 3 times -1 minus -1 to the third. Should be -3 minus -1. That's really +1. I get back -2. And we'll do the same thing for 1. This is 3 times 1 minus 1 to the third. Here I've got 3 minus 1 gives me a +2. So I have a local, sorry, lost my place here, a local minimum we said. Oops, let me clean that up a little bit. A local minimum, and I'm just going to give the coordinates here, -1, -2. I have a local maximum at 1, +2. So here's everything that I can gain out of that first derivative. And this is all stuff that we've seen before. It's just we're doing a bunch of other stuff along with it too. So all right, I've conquered the first derivative. Now we got to talk about the second derivative. So let's see. I'm gonna run out of room here real quick. That's okay. So we said f prime is 3 minus 3x squared. F prime of x, this is really 3 minus 3x squared. So my second derivative, f double prime of x, that is equal to -6x. So just like I did with the first derivative, I want to find places where my second derivative is equal to 0, places where my second derivative does not exist. So I'll take -6x, set it equal to 0. That gives me x equals 0. So there's one possible inflection point. F double prime, again, look at f double prime. Here we have yet another polynomial. So f double prime is a polynomial. It exists everywhere. We're not going to have any additional partition numbers here. So let's go make a number line for our second derivative. Here's f double prime. We only had one possible partition number of 0. And it might not be a bad idea to write the behavior of our second derivative. We set our second derivative equal to 0 there, so I'm going to put a little 0 right above that. And I just need to take a number on either side of 0, plug that into my second derivative here. So f double prime, how about of -1? This is -6 times -1 gives me +6. So my second derivative is positive, which means that my function must be concave up on that interval. Then I need a number on the right-hand side of 0, so how about +1 this time? negative 6 times positive 1, which is negative 6 this time. So my second derivative is negative on that interval, which means that my function must be concave downward. So that tells me a lot here about my graph. I'm going to have to skip over this example. We'll come back to it later, though. This tells me that my graph is concave up on negative infinity to 0. It is concave down on 0 to positive infinity. And then, well, right here at 0, if I look at the behavior on either side, we have a change from positive to negative. That means that x equals 0 is the location of an inflection point. So I'll need to take 0 and plug that into my original function, which, boy, I don't remember what that is. 3x minus x to the third. So 3 times 0 minus 0 to the third. I'll have 0 minus 0, which gives me 0. So that means I have an inflection point at 0, 0. And at this point, we've gathered as much information as we possibly can. We've looked at the original function, we've looked at the first derivative, we figured out where it's increasing and decreasing, found the local extrema. We looked at the second derivative, figured out where it's concave up, concave down, found our inflection points. That's everything. Well, almost everything. You may also want to look at the end behavior. For a problem like this, though, I don't think it's it's not necessary. It might be helpful, sure, but I don't think it's necessary by any means. But I'm going to take all this information and summarize it. Let me highlight this so that we know to look here. It's important. I'm going to take all my information and write it down in one spot so that I have all of it right in front of me. So we said earlier the domain was negative infinity to positive infinity. We said we had no vertical asymptotes. We had no horizontal asymptotes. Let's see, our function was increasing, I believe, negative 1 to positive 1. Let me double check, though. Oops, our function was increasing, yep, negative 1 to positive 1. Increasing on negative 1 to positive 1. Our function is decreasing everywhere else. So that's negative infinity to negative 1 and 1 to positive infinity. We had a minimum, let's see, should be at, oops, I don't know why I wrote main, minimum at negative 1 comma negative 2. I don't remember. Negative 1, negative 2, and a max at 1 comma 2. Max at 1 comma 2. Our function is concave up on negative infinity to 0, concave down on 0 to positive infinity. We have an inflection point at 0, 0. Okay. So we found all of the information, which is great. That's awesome. Now we just got to make sense of it all. Now we just got to sketch a graph. So here's my coordinate axis. Most of my stuff relies around the origin, it appears. So let's say 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. I will generally just kind of start from the top. There are some things that I think are more helpful than others. So for example, I think asymptotes are tremendously helpful when you're making your graph. This time we don't have any, but usually that's where I'd recommend you start. If you have any asymptotes, go ahead and sketch those in. We'll do one like that in the next video. If you have any local extrema, I would plot those so I have a minimum at negative 1 comma negative 2, negative 1, negative 2. I've got a minimum right here. I'm going to do two things here. First of all, I'm going to make a note to myself that that's a minimum. Because there's so much going on here, I think it's helpful just to remind myself of, oh, hey, that's going to be a minimum. The other thing I would do, because it's a minimum, I would just make sure we understand the behavior of the derivative exactly at these points. Minimum, we said our derivative was 0 right here. So we have a horizontal tangent line. I'm going to sketch in that horizontal tangent line at our minimum. And then our maximum we had at 1, 2. Same idea there. I have a horizontal tangent line. And I'm going to make a note that that is a local maximum. Concave up and concave down. I'm actually going to come back to those in just a second here. But I'm going to look at inflection points. I think that's the other thing that I would definitely plot right away. I have an inflection point right here at 0, 0, and I'm just going to make a note that that's an inflection point. At this point, you can look either at where your function is increasing or decreasing, or where it's concave up or concave down, or both. I tend to think that using concavity is a surprisingly helpful way to graph these functions, because if you look at where a function is increasing or decreasing, I feel like that's built in to your minima and maxima values. We won't always have minimum and maximum values, so we may have to look at those intervals. But this is a polynomial. It's a relatively straightforward function. Yeah, we can go ahead and just look at our min and max values. On the left-hand side of 0, so on the left-hand side of 0, we said our function was concave upward. So here's our inflection point right here. I'm going to draw a graph which is concave upward. I know that looks something like this. And I know that this point right here has to be my minimum. So okay, it's concave upward. It's going to look something like this. Here's my horizontal tangent line. And actually, maybe we would even start right here. Here's my horizontal tangent line. And then it's concave upward. It should look something like this. On the other side, we said it was concave downward on 0 to positive infinity. And we said, okay, here's my maximum right here. We have that horizontal tangent line, so I think I'm going to sketch that in first. There's my maximum, my horizontal tangent line. And after that, we're sort of just going to connect the dots in a way that makes the most sense. And actually, I'm not thrilled with how that turned out. That's pretty good. That's about as good as we're going to get here. And then concave downward, we should look something like this. Be careful you don't draw a straight line there. Straight lines have no concavity. We want to make sure that our graph has concavity. It's kind of opening downward, so to speak, here. And at this point, there's our function. We have a graph which is concave up on the left-hand side, concave down on the right-hand side. I see my minimum and my horizontal tangent line there at -1. There's my maximum, my horizontal tangent line at +1. There's everything I have. So this was one of the simpler problems that we'll look at for as far as these types of problems go. Polynomials tend to be nicer functions to work with. Just the calculations tend to be easier. The derivatives are nicer to work with. There's not as much odd behavior going on there. It's just smooth curves throughout. But in the next video, we'll look at a rational function, and that deals with, okay, what happens if we have asymptotes? How does that change our procedures, if any? Then we'll also look at an instance where our function is not differentiable. So, okay, what does that look like? How is that going to impact our problem? So please, I would encourage you to take your time with these problems. This polynomial, I said this is one of the easier ones, and it took me 2 pages to do it. So take your time, go slowly, and organize your work. If you can have all of this information, I might honestly just write it down on a separate sheet of paper or off to the side in your margins. Have it somewhere handy so that you can refer to it at the end of your problem when you're ready to go ahead and make the sketch of your graph.